This video is part of an online course of multivariable calculus, and I'm going to solve one example that shows how we can use change of variables to solve a double integral. So let me start. We're going to compute the double integral of x squared y dx dy by changing to u equals to x and v equals to x and y. I know we never think of doing this change of variable to compute this integral, but it will illustrate the concept. Okay, so let me start. I'm gonna change everything, into u and v. Okay, so the first step would be the area element. Okay, I'm gonna calculate, because u and v are given in terms of x and y, I'm gonna do the Jacobian of u and v with respect to x and y. So the Jacobian is what? Is determinant of this matrix. U with respect to x, u with respect to y, v with respect to x, v with respect to y. So u with respect to x is just 1, with respect to y is 0, v with respect to x, v with respect to y. So the Jacobian is just x. Okay, and so I'm gonna say that the u dv is absolute value of the Jacobian of u and v with respect to x and y dx dy. So du dv is equal to absolute value of x dx dy. But since the bounds for x are from 0 to 1, that's why I can remove the absolute value, because x is positive, so this would be equal to just x. Okay, so absolute value of x is just x. Okay, so what happens to integrand? Integrand is what? Is x squared y dx dy. Okay, so I can write this as x times xy dx dy. So x is u, xy is v, and then dx dy. So if you remember from the previous video, I say that the Jacobian of u and v with respect to x and y and the Jacobian of x and y with respect to u and v are inverse of each other. So I can write this as dx dy is equal to 1 over x du dv. So I get 1 over x du dv, and x is equal to u, so I get v du dv. Okay, or dv du. So I have the double integral of v du dv over the region R. Now let's see what's gonna happen to the region R. The region R in here is what? Let me graph it. So this is x, this is y. So x is from 0 to 1, y is from 0 to 1, it's square. Okay, so the third step is to find the bounds in uv coordinates, uv plane. Okay, so to do that, we just need to understand the edges. Understand edges of the region. The region, as we discussed, was x, y, just a square, because x was from 0 to 1, y was from 0 to 1. Okay, now let's see what's going to happen if we transform it using the given transformation. So it would be what? In the uv plane. Okay, so I'm going to start with this edge. On this side, as you see, y is equal to 0, when I plug in y equals to 0, v would be 0. So I have this part. Okay, so this edge would be like this part over here. And then I'm gonna consider this edge. This is x equals to 1. X equals to 1 would be u equals to 1. So I get this side, which is u equals to 1. Then I have this side in here, which is what? Which is y equals to 1. When y is equal to 1, I get u and v. Both of them are equal to x, so I get u equals to v, which would be this side, u equals to v. And let's see what's gonna happen to this side. This side is basically x equals to 0. When x is equal to 0, u would be 0, also v would be 0. So u and v would be 0, 0, right? U is 0, v is 0, it's just this point. So you see, basically we just shrink this one to a point, and we get this shape in here. Okay, so now I want to set up the bounds. So I have the double integral of x squared y dx dy from 0 to 1, 0 to 1. It becomes what? The double integral of, the integrand was v du dv, v du dv. I'm going to set up the bounds for du, so I need to have a parallel line to the u-axis to cut the region and see what are the first point and second points. Okay, so the first point lies on this curve, which is u equals to v, and then the last point that leaves the region would be on the u equals to 1. And then I can graph these lines in here, starting at here, just to cover the whole region R. Let me say that this is the whole region R. Okay, so v would be equals to 0 to v equals to 1. Okay, now let's solve this one. When I'm taking the inner integral with respect to u, v is just a constant. So I'm gonna write the outer integral, then it would be v u, and then u is from v to equals to 1 dv. So I get what? I get v times 1 minus v times v, so v squared, and then dv. So it would be v squared over 2 minus v cubed over 3. From 0 to 1, plug in 1, 1/2 minus 1/3 minus 0, which is 1 over 6. Okay, that's how we use change of variables to transform the area element, the integrand, and also the bounds. Okay, let me give you just one observation, which is really actually cool. So observation, and the observation is this: to find the bounds on this integral. So after I transform the integral like this, I'm gonna see that to find the bounds for the inner integral, and the inner integral u varies and v constants, because we are taking with the integral with respect to u. So u varies and v is constant. V was equal to xy. So this is constant, meaning that xy equals to some constant. An equation of that is hyperbolas. Okay, so if I have my region xy, which was basically a square of side 1, then I have some hyperbolas equals to some constant. So I have like these hyperbolas. I can slice my region like that. When xy equals to, for example, 0.1, xy is equal to, for example, 0.2, something like this, right? So when I want to set up the bounds, I can say what? V du, and then I say that these hyperbolas, they enter the region at this point and they leave the region, for example, at this point. This point lies here, which is u equals to v, right? So this is u equals to v, because let me graph it with this. So they enter the region R here, and here is x equals y equals to 1, which would be u equals to v. So I have u equals to v here. And then they leave the region, they leave R here, and on here x is equal to 1, which is basically u equals to 1, right? And then I say that, okay, what is the smallest, what is the largest hyperbolas that I can get? The smallest value of xy, because I'm gonna set up the bounds for v, right? The smallest value for v would be like this hyperbola in here, which is what? The smallest value of v, which was xy, is when xy is 0, right? And then the largest value for x and y to cover my whole region would be in here at this point, which would be xy equals to 1. So we can set up the bounds like this, and I can say that slicing the UV triangle by horizontal lines would be corresponding to slicing the region R by hyperbolas. So let me write this. Slicing S, which was what? Which was this triangle that we get in UV plane by horizontal lines, where on horizontal lines we have something like this, that u varies, as you see, and v is constant. If we slice the region in the UV plane by horizontal line, it corresponds to slicing R by hyperbolas. So the region R in xy plane, we slice it by hyperbolas like that. It was a very cool observation. You can set up the bounds by considering exactly your transformation, or instead of doing this in here, you can basically transform the edges of your region into UV plane and set it up the bounds in the region in UV plane.